And the speaker is our previous member of Sinha. He's going to Syracuse for his new postdoc. And today we got him talking about electro boson fusion searches at LHC for various things. The EW-kinos and lepton dark matter, and probably stop with the relatively light masses. So let's welcome the speaker.
Thank you. It's great to be back after a month. Okay, so a lot of this work is, of course, done with the group here. So this is probably a good opportunity for a survey of where we are in terms of these searches, which I think will be very crucial going into the future. Crucial techniques to search for new physics at the LHC, and I hope I'll convince you why. And the particular arena that we'll be using vector boson fusion searches for is supersymmetry. We're going to study different states, supersymmetric states, Electro-kinos, dark matter, top squarks, leptons. Okay, so let me just, okay, so I'm cutting off at the top and the bottom, but okay. So Susie at the LHC, that's the title of the slide up here, which you cannot see. But these are the different kinds of search methods that we have for supersymmetry at the LHC. The first one over here is the Cascade decays of Squarks and Gluinos. This is the classic search technique. You produce Squarks and Gluinos in copious amounts in this color machine. You expect that these heavy supersymmetric states will finally decay down and give lots of jets, leptons, and various other final states. And then you use various methods, endpoint methods, etc., to search for the traces of these particles. The second kind of avenue that is very important is, now that we have discovered a Higgs boson, to study in detail the physics of the Higgs and pick up new signals for new physics from Higgs physics. And then these topics in red are the ones that I'm going to talk about. Direct probes of the electron receptor. And of course, there are huge challenges for this, mainly coming from a very intuitive reason. Your collider is a color machine. You're colliding protons, and therefore non-colored sectors are difficult to search for. The same thing goes for direct probes of leptons. This one is a bit of a special case, direct probe of top squarks, and I hope I'll convince you that vector boson fusion techniques are, in fact, very promising for the search of top squarks in certain regions certain crucial regions of parameter space. And the last one over here is, I'm going to talk about this at the end, but this in spirit is very similar to this up here. So suppose you produce a top squark at the LHC, and then you look at its decay products and try to pick up traces of new physics there. Okay, so this is the kind of so to look at the very first topic that I mentioned, the production of squarks and gluinos, and then cascade decays. Here's basically what happens. So you have the collision of these protons, and you spit out a squark or a gluino, and these particles start cascading down to the lightest supersymmetric particle. We're going to talk about RPAC and conserving models. So this lightest supersymmetric particle is protected by symmetry, and it's a good dark matter candidate. Along the way, the heavy states that we started with give out leptons, jets, and therefore the strategy is to look for multi-jet, multi-lepton final states and find these objects. There are various challenges here. For example, one has to worry about supersymmetric combinatoric problems, lots of background issues, and we have worked extensively in providing new techniques for those kinds of searches. But here's the situation right now. This is an atlas plot with around 6 inverse femtomorn of data. There's a corresponding plot for 20 inverse femtomorn of data, but it's more or less the same story. And the story is that we have not seen, so over here you have a Gluino on the x-axis and a squark mass on the y-axis, and everything that's to the bottom left of this red curve is ruled out. And what you see is that we have not actually seen squarks or Gluinos in this mass range. For similar masses of squark and Gluino, the exclusion bounds almost reach 1400 GeV. The situation with the top squark is slightly different. One can also produce top squarks, and these guys decay down again to the lightest supersymmetric particle. It gives jets and leptons. This very messy plot kind of summarizes the exclusion region for top squarks, and you can see that the exclusion bounds are a lot weaker than squarks and Gluinos. Squarks of the first 2 generations and Gluinos, they're order a few hundred GeV as opposed to 1400 GeV. And again, there are lots of assumptions that go into these exclusion plots, and I'll get to these in more detail. But the story is that we have not seen these colored supersymmetric states at LHC yet.
Sorry, what is the red star?
Oh, I'll get to that. Okay, so this begs the question, well, should we now concentrate on the various complementary searches that I had on that list going down? Okay, so the second item on my list was 125 GeV Higgs, and this will probably be a slightly provocative statement in many places. I would say that this Higgs looks supersymmetric. The best bet is it's a decoupled supersymmetric Higgs. Okay, the reason I say it looks supersymmetric is because it falls within the MSSN window of around the lowest bound being the left bound, which is 115 GeV, and the highest bound being around 135 GeV. So this falls there. And I think the observation of a weakly coupled Higgs is pretty much the death of technicolor models. Again, one can tweak these things to work, but I think in terms of philosophy, the fact that you saw a weakly coupled Higgs does not really tells you that nature is not preferring a strongly coupled system to give you electron symmetry. The case with the other candidates for symmetry breaking, such as little Higgs, etc., I think the jury is still out on those models. Practitioners of these models will claim that they work at least as well as a supersymmetric Higgs does. But again, I think supersymmetry is so well motivated from other reasons that this is really the case that I'm not sure about that. The value of 125 GeV Higgs is an intriguing value. It has a lot of bearing on what kind of supersymmetry we think exists in nature. For example, there is a huge difference in outlook between 118 GeV Higgs, 125 GeV Higgs, or 130 GeV Higgs. Much of it comes from the fact that in supersymmetric theories, the tree-level mass of the Higgs is given by your Z mass. So the rest of it is coming from quantum corrections. This particular statement is true within the MSSN. One can, and therefore, okay, so what you have over here is that if you're within the MSSN, the tree-level value requires large quantum corrections to take you up to 125 GeV Higgs. And there are raging debates over naturalness because of that, because of these large quantum corrections that are required. One can trade these large quantum corrections by going to a model which has more stuff in it. For example, the NMSSM or the MSSM with non-decoupled ions, etc. And in that case, there's extra contributions to the tree-level Higgs mass, and therefore the naturalness or fine-tuning burden is a lot lesser on the quantum corrections. And one can in fact make this kind of a plot where you have more fine-tuning on the x-axis and more tricks or more moving parts in your model on the y-axis. And perhaps the MSSM is more fine-tuned, but it has less moving parts than, for example, the NMSSM or E1s. But all of this tells us that the value of 125 GeV Higgs is really already telling us a lot about the kinds of supersymmetry models that nature might prefer. And it's fair to say that Higgs decays will be under strict scrutiny for a long time. We will be looking very carefully to see departures from standard model predictions in Higgs decays. The status right now is it looks like a decoupled supersymmetric Higgs. Its supersymmetric cousins are probably very heavy. Its branchings are tending towards standard model branching. And of course, it's still important to keep an open mind and study non-decoupling scenarios. And there have been papers where people have argued that the Higgs, the supersymmetric cousins of the Higgs are actually light and still obey all limits. Okay, so here's a slide that I got from some Michael Peskin talk. So basically, this is the kind of spectrum that one can start to look at. You have over here the various non-colored states, the neutralinos, chargino, light, and then you start having the colored states up here somewhere very heavy. Okay, you can ignore this value of M3 for now. That really is not very relevant for this talk. But these kinds of spectra come in various names. So, for example, split, mini-split, simply unnatural, etc. But the basic idea is, look, we have our colored sector up here very heavy, and perhaps the neutralinos and gauginos, perhaps even the gluino is not out of reach. And that essentially points out that what a particular search strategy would be to ignore these heavy colored objects for now, simply because we haven't found them yet. And perhaps try to concentrate on finding these guys over here. Okay. So my slide got cut off a little bit. Over here it says electroweak sector, and the question is, can we probe the electroweak sector? And in fact, non-colored objects, leptons, taus, charginos, and neutralinos directly. And this has a lot of, it's an important question because it has a very robust connection to dark matter physics. The question of whether the neutralino is albino, Reno, or Higgsino would determine a lot of things. In fact, it will tell you a lot about the cosmological history before Big Bang nucleosynthesis. The annihilation cross-section of these dark matter particles depends mainly on colorless particles, other particles such as leptons, taus, charginos, neutrinos, because the annihilation cross-section often depends on whether there's a light lepton or a light neutralino, chargino that's very close to your dark matter. And I'll talk about this in more detail. Okay. So I want to talk a little bit about SUSY dark matter, especially within the NSSM. Here's the neutralino mass matrix. You have basically three limits that you can go to. The pure Bino limit is when M1 is a lot smaller than M2 or mu. And in that case, the neutralino is essentially albino. The case where M2 is a lot bigger than the other two, M1 and mu, is when it's a Gluino. And if mu is a lot smaller than M1 and M2, then you have basically Higgsino dark matter. And all of these are well motivated from various points of view. So I'll just start with Higgsino dark matter. The most obvious motivation for this is natural supersymmetry, because the Z mass, mu, and MH op are related by this relation in supersymmetry. And if you don't want large cancellations between different sides of the equation, then you expect your mu to be order n Z, and therefore you expect light mu since mu is controlling the mass of your Xenos, you expect white Xenos, and therefore dark matter. This has been studied by various groups for quite a long time. Last year, we took a slightly different approach to dark matter and argued that the cosmological modulate problem also independently motivates white dark matter. And this happens because of, in the simplest toy model, perhaps, of modular sterilization in type 2e, which is the KKLD model, in order to avoid the cosmological gravitational problem, you end up with a pure dark matter in various regions of parameter space. The problem with dark matter is, of course, that you only get its annihilation cross-section to give the correct Rayleigh density if mu is order 1 TeV. That's in a thermal scenario. So if your history is thermal, if dark matter freezes out, comes to thermal equilibrium, freezes out, and that sets the Rayleigh density, then you need Xenos of order 1 TeV in mass. And there's in principle nothing wrong with that, except it would clash with the idea of fine-tuning that I laid out before over here, and also the fact that it's hopelessly out of bounds for both detection both at the LHC and for any dark matter experiment in the near future. And therefore, it's important to, for example, in this case, to concentrate on non-thermal sub-TeV dark matter, which we studied in detail.
I mean, is that true for direct detection also?
Direct detection, if it's a pure Xeno, then the scattering cross-section is suppressed. However, if you want to really detect it, you're going to run into, the detection levels will be at a point where your neutrino background will start kicking in. So either way, you never go, if it's a pure dark matter, you're really out of luck. To get direct detection limits, you need a Xeno mixing of, the Xeno should not exceed more than 10%. If it exceeds more than 10%, it's ruled out. If it's pure Xeno and
Yeah, so there's a blind spot when it's pure Xenos.
Right, and I'll come to that when I talk about this. Okay, so pure dark matter is also well motivated from various angles, and it comes up in simply unnatural SUSY statements, like these kinds of scenarios. The situation with the thermal, we know, is very it's even worse than a Xeno. You need a 2.5 TeV thermal Gluino to mask the Rayleigh density. And again, one can study non-thermal sub-TeV dark matter, but there have been recent studies where these candidates start clashing quite strongly with indirect detection problems coming from Fermi. So there's a lot of interplay between direct and indirect detection dark matter, cosmological history, and the mass scale of dark matter. The Bino dark matter has an opposite problem. It usually gives too much dark matter because it doesn't annihilate too efficiently. And again, there are various ways to get around that. Within a thermal framework, one would do, for example, to boost up its annihilation cross-section, one would introduce states that are close to it and that can help in co-annihilation, or perhaps a resonance region where the mass of the pseudo-square Higgs is like twice the Bino mass, etc. So again, these are some corners of parameter space where one can get a thermal Bino, and I will talk about them later. Or one can go for a non-thermal Bino dark matter through branching from modulus decay. And this modulus can also be a visible sector modulus. Okay. The third option is not to go to any of these extreme limits. So you don't go to M1 much lesser than M2 and mu, or M2 much lesser than M1 and mu, but rather you mix them up in such a way that you get a well-tempered dark matter that just gives the correct Rayleigh density. And the philosophy here is that the Bino gives you too much, and the Higgsino or the Wino gives you too little. So therefore, you mix them together, and you get just the correct density from these kinds of well-tempered scenarios. And again, there are various bounds, and so there are various bounds on these things. So for example, a Beano Xenon dark matter starts getting bounded by direct detection cross-section. Beano Xenon, again, depends on how much Xenon there is.
Sorry, when you say visible sector modulus, you mean what?
Oh, sorry. When I meant over here, you could get the Beano dark matter by branching of a modulus, and that modulus could be a visible sector one. What I mean over there is that anything that interacts stronger than gravity is visible sector. So you could build a visible sector model where you have a singlet phi that couples to the MSSM, and this coupling is such that this phi decays late, and the branchings work out such that you get the correct Beano.
But you said this is another model similar, but it will still couple more strongly than gravity.
Yes.
So the kind of coupling would that be?
One could, for example, have a singlet, and then the standard or MSSM, and then you have various connector fields. So you need fields that are charged both, that are charged under the MSSM and also coupled to the singlet.
But can you still make it long-lived?
You have, well, again, so that's the point. It turns out in our paper that we wrote in December that the Yukawa coupling for this thing has to be order 10 to the minus 6 or 7.
Okay.
So there is some fine tuning there. And also you can suppress these branchings by having them loop suppressed. So you can get loop suppressions there. But I think the robust statement is if you want a visible sector modulus, then the Yukawas have to be order 10 to the minus 6. It's a replacement for the weakness of drag. Okay, so this ends my SUSY dark matter introduction. I think it's fair to say that SUSY dark matter can be studied from 3 different angles. One, which is very popular, is monojet searches, and I will not talk about that here. Another one is the production of colored particles cascading down to the LSP. I have argued that Squarks and Gluinos, because we have not observed them yet, we should look at, this is probably not the correct method right now, unless one talks about the top score, which is still, the exclusion bounds on that are still weak. And the third one that I am going to talk about for the next few minutes is direct probe of the electron receptor. So one directly probes the SUSY dark matter without going through the color receptor. Okay, so why is the direct probe of the electron receptor so challenging? Well, because if you look at the production cross section, so these various contours give you the production cross section at the late C as a function of the mass of these particles. You see that you see that. So the production of the colored particles is a lot more than the production of these guys over here. And because of that, it's a very tough game. So I believe this axis is in picobars. Okay. So what kind of searches exist for neutralinos and charginos? This is the latest Cms plot with 19.5 inverse 71 of data. What's going on over here is that you have a proton-proton collision, and you produce neutralinos and charginos, and they cascade down to the lightest neutralino, and they do so via a light lepton. The reason you need a light lepton is it gives you leptonic final states. You need that because the production cross-section of these neutralinos and charginos is so low that leptonic final states are kind of your only hope to start reducing color background. However, what this does need is that you need a light lepton to start to basically sit between whatever you're producing and the final LSP. If you look at the contour plots here, so on the x-axis is a chargino 1 or neutralino 2, and on the y-axis is neutralino 1. And these are the exclusion bounds. These are all tri-lepton studies. The green curve over here is the strongest one, where the lepton left is sitting between neutralino 2 and neutralino 1. Because it's sitting there, you have a lot of branching to leptonic final states. The moment you take away a light lepton and you don't have these leptons in the final state, your exclusion bonds go all the way down here. This brown plot over here is the corresponding thing for neutralino 2 charge 1 with no lepton. It's going directly to W and H. And the lack of leptons basically makes this a very tough game. Okay, so these are the vector boson fusion studies that we are currently working on. The top one over here is the production of chargino 1 and neutralino 2. So the chargino 1 and neutralino 2 in this study will be Gluino. And over here, this is the direct production of neutralino 1. And in this case, neutralino 1 will be either a Gluino or a Hexino or a mixture of Gluino and Hexino. And these two studies over here are work in progress. Number 3 is lepton production via VBF. And number 4 is top score production. Notice that everywhere we have 2 jets coming in, and those are the vector boson fusion jets, which I'll talk about. Okay, so to start with, the 2-jet plus MET analysis. So the 2-jet plus MET analysis is this one. What one does is you have your collision, PP collision, and then this is the kind of Feynman diagram one talks about. So you have these quarks coming in and going out, and they radiate off a weak boson. This weak boson comes inside, and then there's the exchange of a chargino, and it gives off 2 neutralino 1s. Okay, so that's why your final state has 2 jets, it's 1 and 2, and these 2 neutralino 1s, which are basically missing energy. On the eta phi plane, if you look at the 2 jets, then these are 2 forward tagging jets. Okay. Now, just to back up for a second, there are bounds coming from there are bounds coming from other experimental techniques on Gluino or Hexino dark matter, and these are coming because of the charge track analysis. Basically, if you have Gluino or Hexino dark matter, then the chargino goes to a neutralino, and there's a pi, and you can see the track of this pi. And the PT of the pi basically depends on the mass separation between the chargino and the neutralino. And these provide complementary exclusion bounds for chargino and for Gluino and Hexino dark matter. I don't have the plot here, but this is an interesting study, so I just want to kind of draw it. So delta M, and this is the mass of chargino. The Atlas bounds are currently something like this. Okay. So this is kind of a left bound here. Now, delta M, the mass separation between chargino and neutralino, can be worked out and it has been worked out to 2 loop level, and what it looks like is something like this. Okay, so something like that. And the statement is, so and this delta M turns out to be around 160 MeV. And this mass comes out to be around 200 GeV, maybe 250, 240 GeV. So the charge track analysis coming from Atlas is already putting exclusion bounds on the mass of the chargino, mass of the Gluino. And the latest result published in July with 20 inverse femtogon of data is order 240 GeV chargino being excluded. So one needs to keep an eye on this particular study. For us, this is important. For us, what we'll be doing is we'll be taking, because the mass separation between the chargino and the neutralino is so small, order 100 MeV or so, we'll be taking the charginos to also be dark matter. Okay, so when we calculate the cross section in this 2-jet plus MET analysis, we'll be not only taking the production cross section of this kind of diagram where you have neutralino 1s in the final state, but also these kinds of diagrams where you have chargino 1s in the final state. Okay, so So that's for the 2-jet plus met analysis. This is the 2-jet plus 2-lepton plus met analysis. So if you want, it's this one over here. So what we're doing over here is, again, you have your jets coming in, weak bosons being radiated off. And then you have the production of charginos. And in a spirit similar to the searches at CMS, you put a light star or a light lepton in the middle, and you get the tonic final states along with met. So therefore you have 2 leptons plus met plus 2 jet. If you look at the 805 plane, then the orange spots are the forward tagging jets, whereas the leptons are much more central. Okay, so these studies are based on 2 papers that we wrote. Here's the first one. Lots of people here. We also had Alfredo Barola from Vanderbilt University. And this study over here, which is a subset of the previous set. What kind of production cross-sections are we talking about? For the 2-jet plus 2-lepton plus met study, here's the production cross-section contours. So this axis is in femto-1, and here's the mass scale in GeV. And you can see that, of course, as you increase the mass of your particle, the production cross-section goes down. But we're talking about production cross-section of order a few femto-1 in these cases. Here's the corresponding thing for the 2-jet plus met study. And this panel over here is 8 TeV. This panel over here is 14 TeV. The different contours in this plot correspond to the identity of your neutralino 1. When it's a pure Gluino, you have the highest production cross-section, because that's expected because you have a weak boson fusion here. When it's a Higgsino, there's an order factor 4 reduction in production cross-section. And then these contours over here are when the Higgsino fraction is decreasing in neutralino 1, and the Gluino fraction is correspondingly increasing. So you start going from 100% Higgsino to 80%, 60%, 40%, and 20% Higgsino. And it keeps going down. So this is the kind of kinematics that we have for vector boson fusion processes. This plot over here is PT of the leading jet. The black dotted contour over here is signal. Again, this is, one can draw kinematics for different studies that we did, but the kinematics is roughly, this kind of kinematics is roughly similar no matter what kind of final state you consider. So here's the kind of PT of jet that we obtain for signal and background. So you can see that there's a high PT forward leading jet, a PT of jet 2, and these 2 curves over here, this left one is the dijet invariant mass of the tagging jets. And again, you can see that the signal typically has a larger dijet invariant mass. And the right panel over here is the met. Okay, and again, the black dotted histogram is for signal, whereas these are for the background. And again, you see that you have much larger met in this case, because your final states are supersymmetric. Okay. So this is the benchmark point that we chose for the 2-jet plus 2-lepton plus met study. The chargino and neutralino 2 were at 180 GeV, neutralino 1 was at 90 GeV, and we put a lepton in the middle such that the mass separation between the lepton and neutralino 1 was ordered 30 GeV. Okay, so this is the kind of thing. And these 2 plots over here give you the dijet invariant mass on this side for the di-tau study, and this is for a di-lepton study for this mass spectrum. This is an 8 TeV study. We are currently upgrading this to 14 TeV.
What are you plotting on the x?
Right, so on the x-axis, it's a dijet invariant mass. Okay, so you have these 2 tagging jets, and this is and you can see that in the large dijet invariant mass region, the blue region is your signal, and there's an enhancement in the large dijet invariant mass region. The kind of selections that we took for this study, we took 2 jets with large PT jet 1 bigger than 75, jet 2 bigger than 50, because we want these to be forward high PT jets in opposite hemispheres. So that's the classic VBF signature. We took delta eta to be bigger than 4.2 and eta 1 times eta 2 less than 0. We can see from the kinematics that the signal prefers large dijet invariant mass, so we put a cut at 650 GeV. It prefers a large MET, we put 75 GeV for this particular benchmark point. And because it's a 2 jet plus 2 lepton plus MET study, we want to reduce TT bar background, so we vetoed on P jets and selected at least 2 leptons. So this is work in progress. This is the plots that I presented before were HTV study. Our initial calculations at 14 TeV, essentially, here's the 5 sigma mass reach. You can see that over here, so this is the current existing exclusion plots from CMS in the 2 jet plus 2 mu final state, and over here for the 2 jet plus 2 tau final state. And these are our benchmark points at 300 inverse femtobarn, 5 sigma discovery level. You can see that our performance is particularly suited to these compressed regions, and this will come back again and again. Compressed regions where the mass separation between the lepton and the neutrino 1 is not that much. And that's where non-vector boson fusion studies start degrading heavily. In the rest of parameter space, our approach is complementary to non-VBF studies. So this is the 2 jet plus MET final state study. This is dark matter plus, this is VBF dark matter study. And again, one has the same kinds of selections. You take your 2 tagging jets, large dijet invariant mass, and because this is a pure 2 jet plus MET study, so you don't do any leptons, there's no light leptons, nothing. You veto on leptons, veto on B jets. You take a central jet veto to further reduce TD bar background, and take large MET to optimize each mass of neutrino 1. Here's a MET plot for the main sources of background. The main sources of background over here are W plus jets. Z plus jets is reducible background. Here's the yellow histogram. And these dotted black lines over here show you the distribution for 2 different masses of neutrino 1, 100 GeV and 50 GeV. This basically summarizes what we found. This is an 8 TeV study. Over here is the mass of neutrino 1. In this case, we took the best case scenario to be Gluino. And here's the significance. These 2 green lines tell you the 3 sigma and 5 sigma reaches. And what we see over here is that we expect to see order 600 GeV Gluinos with 1,000 inverse femtobarn of data at 14 TeV. One can also take the 2 jet plus MET study and obtain from there the relic density of dark matter. So what one does is, the relic density is a function of the composition of neutrino 1 and its mass. We can extract these 2 information from the composition depends on, the composition is going to affect the production cross-section, and the mass is going to affect the MET cut. And using these 2 pieces of information, we can draw relic density versus mass contour. And we see that for the blue contour over here is for Gluino dark matter, and this is the 1 sigma contour relative to some benchmark value. Okay, so to summarize this part of the study, I think it's fair to say that the 2 jet plus MET study is exceptionally free of trigger bias. We find that Gluinos and Xenos can be probed up to 600 or 400 GeV, regardless of the existence of light leptons or lighter states. And this is theoretically important because we are not, in the 2-jet plus MET analysis, we are not relying on the presence of other light states, which is important in the naturalness or split SUSY programs. A few comments on the effect of pileup on our studies. So this is an ongoing study being performed by Ken and collaborators at Baylor, and they're basically using Delphis to study the MET degradation with pileup. They're selecting Z plus jet events and studying the perpendicular and parallel components of the hadronic recoil. And what we see over here, so the blue line is with 140 pileup, the red is with 50, and the black is with 0. And what we see is that this is a preliminary result. There's a 10% effect on energy scale and 50 GeV on resolution. So 10% effect on energy scale, 50 GeV on resolution. Translated to our mass reach, this does not have a very strong effect on the mass reach. Perhaps 4% in signal significance. We would also benefit from extended tracking. This will be very crucial to determine the jet vertex, to reject pileup jets, but also because in the 2-jet plus MET analysis, if you remember, one of the major backgrounds was the W plus jets. And in order to reject that, we had to veto leptons. But vetoing leptons vetoing leptons is of course not a perfect thing. And in fact, one can see from over here, if you plot, this is Adolf lepton, and the red contour over here is W plus jets. You can see that roughly 30% of leptons fall outside eta equals to 2.5. So we can't veto them, we can't see them. And therefore, extended tracking will enable us to veto these leptons even further and get higher signal significance. Okay, so I'm going to move on to the last part of my talk, which is so the title of this slide is Top Squarks Searches. And there's lots of reasons to study top squarks because top squarks play an important role in SUSY naturalness arguments since they couple significantly to the Higgs. And there's also other reasons such as electronic baryogenesis. We took 3 different approaches to studying top squarks in a number of different studies. The first one, which I'll talk about now, is vector boson fusion processes, and this can be used to study top squarks in a compressed limit, which I'll get to in a minute. One can also look at top squark production via QCD, and in this case we did 2 studies, one where the LSP was a well-tempered Bino Xenon, and the other one where it was a pure Bino. This is a vanilla Bino LSP study. On the exclusion plot plane, here are the 3 studies. The x-axis is the mass of the top squark, and the y-axis is the mass of the neutralino. These are the exclusion bounds coming from Atlas, and they all assume 100% branching of the stop to top plus neutralino. The orange exclusion plot over here is the semi-electronic study, and it has the largest reach. This dotted line over here is the line where the stop mass is equal to top plus neutralino. Okay, so what are the regions of parameter space that one can see? You can see that there's this region over here that is very close to this line, this line of degeneracy, where the current searches have no sensitivity. And that's because when the top squark mass is equal to top plus neutralino, your MET cut, because you rely on MET to identify supersymmetric events, they lose their sensitivity. Okay, so you have basically the final states are on shell with the initial state, and that's why there's almost no significance there. And the way we use vector boson fusion was to study. This region over here is called the compressed scenario. And we use vector boson fusion to study the compressed scenario. The other 2 studies that I talked about fall straight in the middle of these excluded regions. Number 2 study was when the LSP was a Bino Higgs Xenon. So it's represented by the star over here. And I'm allowed to be on this excluded region because we have to remember that these exclusion regions are a product of the cross-section and the branching ratio. So all of this assumes a branching ratio of 100% of a stop going to top plus neutralino. If it's anything less than that, then it starts getting weaker. And in fact, in the most well-motivated cases where the LSP is a correct dark matter candidate, which is well-tempered between B and Xenon, it turns out that you can be right over here and not be excluded of that. Okay, so this is based on this study that is ongoing. And here's the kind of benchmark point that we'll take. This is the vector boson fusion study for compressed TAR square. I put a star over here, but that's actually work in the future. So these are the kind of Feynman diagrams that one can have for vector boson fusion production of TAR squarks. Again, you have a weak boson or a gluon in this case coming off from initial jets, and there's the exchange of a stop, and then you have two stops in the final state. The VBF processes are marked again by the presence of two forward tagging jets. We considered a bunch of different benchmark points for stop and LSP, so 300, 120, 400, 220, etc. Notice that the mass difference between stop and LSP in all these benchmark points is 180 GeV, which is very close to the top mass, which is because we want to study this compressed region. Okay, that's where we really want to prove physics. The main background, TT bar and QCD, we do a semi-electronic study in this case. So we do two jets plus 2B plus 1 electron plus net. So the two jets are coming from the forward VBF jets. The two Bs are coming from the fact that these two top squarks decay to a top and a neutralino, and therefore you have two Bs. And then because it's a semi-electronic study, we take 1 electron and we take net. These are the kinds of selections that we do. Two high PT jets, the usual VBF signature delta eta. We take large digit invariant mass and met cut of 150 GeV. You might ask why met cut is effective in this case. Remember that I argued that in the non-VBF studies, there's no significance here because the met cut is rendered ineffective. Whereas in the VBF case, you actually have a large met cut, which helps your analysis. The reason is as follows. Okay, so I think I'll go over here. The reason is as follows. So these are significance contours on the met and digit invariant mass claim for different masses of stop and LSP. So 300, 120, 400, 220, 500, 320, etc. And you can see that your met has sensitivity because what you're doing over here is actually a cascade decay. So you're actually producing, you're not directly producing top squarks. In which case, if you did produce them directly, then if they're on shell with their decay products, you're out of luck. There's no missing energy there. But because they're being produced from these two high PT forward jets, anything that's transversed is ultimately going to end up as missing energy. And so the difference is between direct versus non-direct production. And you can in fact see that as the mass of the top squark increases, you have sensitivity for larger met. This is an initial plot that we have. This is the plot where delta M equals 10, so therefore stop minus neutralino is equal to order 10 GeV. And this is the stop mass versus significance plot. And the message over here is that with 300 inverse femtomon of data, you have a 5 signal reach of order 400 GeV for the top squarks. So where does that reach fall in current plots? This is the existing CMS exclusion plot for top squarks, and this is the existing Atlas exclusion plot for top squarks that I showed before. This star over here gives you our benchmark point, and you can see that we're evading, because this delta M is order 7 for us, and for this same mass, CMS is only reaching up to delta M equal to order 37. So we're probing regions that are new. And the same thing on the Atlas exclusion plot as well. What's even more interesting to see the projected plot. So this is a projected CMS plot so this is, okay, so the blue dotted line over here shows 14 TeV, 300 induced femtobarn, and then there's it says optimistic. So I got this plot from the SNOMAS, one of the SNOMAS studies. This is a CMS plot. And what you can see over here is that even in the most optimistic scenario, you're not going to be able to probe, without vector boson fusion processes, you're not probing this region over here, which is our benchmark point, because the mass separation is so small. Okay, so one limit of the compressed scenario is when you go down this corridor all the way to the x-axis, and the neutralino becomes massless. So the top squark becomes very close to the top mass, and the neutralino is massless. In this case, what happens is that you actually get back to the usual studies. You don't have met significance here because the neutralino basically went massless. And one can see that in this kind of a significance plot on the MET and MJet plane. So this point is stop equal to 180, neutralino equal to 0. And you can see that the best significance is in fact centered around MET equal to 0. So MET-cut actually loses effectiveness in this region. This is an ongoing study. One can go on the other side of this line and study top squarks that are actually lighter. They go to an off-shell top, or perhaps a charm neutralino, and these we are currently working on techniques to probe top squarks in these regions as well. In the last perhaps 5 minutes of my talk, I want to talk about a non-VBF study. Here's the benchmark point, and this is a non-VBF study. What we did over here is we took the LSP to be a well-tempered Xenon LSP, and as I said before, when one does that, the stop is not going to decay in the vanilla mode, but rather, here's the kind of decay modes it has. Because your Xenon is now light, the stop prefers to decay to neutralino 2 and 3 39% of the time, and also a chargino 53% of the time. And only the remaining 8% is the vanilla decay mode to top plus neutralino 1. And that enables you to study these portions of primary space, which are excluded in the vanilla modes, but are not excluded in these kinds of modes. And why should we look at them? Well, because non-vanilla stop decay modes are important because Xenon dark matter can actually give you the correct relative density. And as we talked about before, for example, pure Xenon dark matter can give you, is important in its own right. And in fact, there have been 2 non-vanilla studies of top squark decays. We did the Xenon study, and there was a pure Xenon LSP study using topness by Michael Bresser and Jesse Shelton. Okay, so these are the kinds of this is the kind of spectrum that we use. So stop going to neutralino 3 or 2, and then decaying down to neutralino 1, or stop going to chargino 1, going down to neutralino 1. Here's the composition of the neutralino 1. So I want to say thanks to Kitch and Wang for the slides in this particular study. Okay, so this is the composition, and these are the decay modes. And the reason we took these are because of these reasons over here. What kind of study did we do? Well, neutralino 2 and neutralino 3 go down to neutralino 1 via our light lepton, and therefore you have leptonic final states. One can study opposite sign, same flavor dilepton distributions, because these 2 leptons that are given off have the same flavor and the opposite sign. When one does that, this is the kind of distribution one finds. This is for signal and background. So this is the final state that we took was 2 lepton plus 2 jet plus 1B plus large MET. We applied a MET cut of 150 GeV, HG cut of 100 GeV. And this unshaded histogram over here shows you the opposite sign, same flavor distribution for signal and background. And the shaded distribution over here gives you the opposite sign, different flavor for signal and background. When you subtract them, you get the red histogram, and you can see the clear presence of an edge, which corresponds to the mass difference between neutrino 2 and neutrino 1. This edge shifts as you change the mass difference between neutrino 2 and neutrino 1, and it also goes up and down as you change your top squark mass, because that affects your production cross section. Here's a summary plot of this study. What we found is that at 8 TeV LHC with 30 inverse 10 to 1 of data, pinohexeno dark matter gives a significance of order 3 for this mass. If one, and this depends on the presence of the light lepton, because you want to do an opposite sign different flavor leptonic study. You need leptonic final states. If you don't have a lepton, your leptonic final state branching ratio goes down, and in fact your significance goes down. So in the heavy lepton scenario, you only get a significance of order 1. And in fact, this motivates us to study this kind of thing at high luminosity LHC. One can also do a co-annihilation study where the BINO and the lepton mass is so small that the emitted lepton has low PT, and in this case the significance is even lower, and this will require a high luminosity study at LHC 14 as well. The take-home message from this part of the study is that the preliminary results are for 700 GeV stops, one can get a significance of 5 sigma at 300 inverse femtobarn in this opposite signed same flavor study. Okay, so I'll move on to the conclusions. I think it's fair to say that vector boson fusion processes provide a direct window to the supersymmetric electric receptor. The reason they're very interesting is you're able to study the non-colored sector directly, and that allows you to be agnostic about the colored sector. So you can take your colored sector to be very heavy, order 20 TeV, order 5 TeV, perhaps just out of reach of LHC. But the direct probe of the non-colored sector lets you be agnostic about that. These are complementary to SUSY searches, therefore, from Cascade Decays or trilepton studies. They're really critical in the compressed regions of parameter space where these complementary studies start to degrade heavily. For the 2-jet plus MET study, what we showed is that we can probe Gluino dark matter up to 600 GeV at 5 sigma level with 1,000 inverse femtobarn of LHC data. For Hexeno dark matter, the corresponding mass is 400 GeV. This is the best case scenario, and the effect of pileup on our studies is under progress. But I think this is very important to stress because we're not relying on the presence of any light leptons, and in fact this is an exceptionally bias-free trigger. And the fact that we are able to probe these particles up to a few hundred GeV should tell us that given the right probing techniques, the LHC is able to probe the non-colored sector quite well. We use this kind of study to find the relative density using the fact that the production cross-section depended on the composition and the missing energy dependent on the mass. These two pieces of information allowed us to get the relative density of dark matter in this study up to 20 or 40% accuracy for Gluino and Xenon dark matter. We are currently studying the production of leptons, the bonds on charginos in heavy lepton scenarios, etc. We showed that the VBF studies can actually be useful in the colored sector as well. The top squark sector is accessible near the compressed limit, where current and optimistic future reaches of CMS and Atlas will not be able to approach. And we have studies that are ongoing for the stealthy, off-shell, and squeeze limits, The stealthy scenario, I showed you the initial results where the met cut loses effectiveness. Off shell and squeezed are on the other side of this degeneracy line. And at the end, I also discussed a non-VBF study, which I think is physically very well motivated. One considers the top squark decays, direct production of top squarks, non-VBF, but then instead of going for the vanilla decay modes, which are excluded up to a large mass, one considers well-motivated non-vanilla decay modes using dilepton distributions. Question for Kuver?
Can you bring the research back? The top.
This one?
No. Next one. The last sentence, the 40% accuracy is for pure Xenon?
Yes.
Is right.
Yeah, because I mean we can see that from the 1 sigma boundary plots.
That was pure.
Yes, that is pure. As you start going more and more impure, of course your study is going to have lesser results.
Oh yeah, that 1 over root 2 that's the Cascade.
Yes, which you worked on.
So it's pure.
Okay.
Because Leaks Cascade has that 1 over.
So I have a question about that. When you lower the soft mass to, say, close to the top mass, you said that the matter is not effective. But do you still have significance there for EW-kinos?
No, not right now. No. So yeah, this is what you get. Your met cut loses effectiveness.
Well, it looks like there's the red color still indicates you have some muscle.
We played with the MJet jet cut over here, and it doesn't look very promising. It looks like you basically go back to the usual case where there's an orders factor of 6 difference in TT bar background cross section and stop.
More questions? Okay, let's thank Kuver again for this very informative talk.